Okay, this is AQA, A-Level Physics, 2020, Paper 1. And just a reminder that sadly I can't show the paper on screen, otherwise AQA will get my channel deleted as they nearly did in the past. 1.1, we're being asked whether or not this decay is possible. So let's think about our conservation rules. Let's go with, well, there's no baryon numbers, are there? So it's just 0 goes to 0 plus 0 plus 0. So that checks out, that's fine. What about a lepton number? Well, pion is a meson, so it's a hadron, not a lepton, so that's 0. Electron has a lepton number of +1. Anti-muon, because remember a normal muon is minus just like an electron, so that's going to be -1. And then we have an anti-electron neutrino, that's also ±1. So actually doesn't look like it makes sense because we don't end up with 0 on the right hand side. So we can say lepton number not conserved. Oh, there's an R that looks like a V as per usual. Ce n'est pas possible. 1.2, state the two possible quark configurations of pi 0. Well, we know it can be up anti-up and down anti-down. Now you might be tempted to say strange and anti-strange as well because, well, they add up to 0, don't they? But actually that doesn't make a pion technically, that makes a phi meson. Phion, I guess? Whatever. So it's not that, so it's just up anti-up, down anti-down. So what about K0 meson and an anti-kaon? Are they the same particle? First of all, the thing that you need to know about kaons is that they have strangeness. So therefore, we say that a kaon has a strangeness of +1. So therefore, the quark configuration of this is going to be down anti-strange. Remember, strange quarks are very strange, which means that they have not the right strangeness, as it were. An anti-kaon has to be opposite in every regard. We know it has the same charge, so yes, that's fine, but we know it has to have a strangeness of -1, so technically it has to be anti-down strange or strange anti-down. That is the quark composition of an anti-kaon. Not an easy question, that one. Okay, 1.4, classic question. Question 1.4. Okay, we're talking about a nucleus. It's been held together by a force. What is the particle responsible for this force? The particle itself must experience this force. Interesting. It would have a rest energy between an electron and half of a nucleon. Is it a kaon, muon, or pion that is going to do that? Well, let's have a think. For a nucleus, well, it's held together by strong nuclear force. This only affects hadrons, so baryons and mesons. So first things first, let's get rid of the muon. It's a lepton, therefore it is subject to or affected by weak nuclear force instead. Cannot be, well, we can say the gauge boson or the exchange particle. Let's go with the exchange particle here, the thing that they haven't mentioned. Gauge boson. So what about the kaon and the pion then? Well, they are both mesons, so they are affected or experience strong nuclear force. So it looks like we're going to have a look at the formula sheet at the rest energies of these particles then. So not often we have to look at the rest energy of these various particles, but let's do it. If we look in the formula sheet, we see that a kaon is, well, we have K0 at 498, K plus and minus at 495. So let's say about, I don't know, 496. We don't need to be super accurate because it's going to be fairly obvious, I guess. Pion, we can see that's about 135 mega electron volts, and we know that it's got to have a rest energy, what did it say, between an electron and half of a nucleon. Okay, so an electron, basically 0.5 mega electron volts, and then a nucleon, doesn't matter which, let's go with proton. They're very similar, they're about 940, aren't they? So about half of that is about 470 mega electron volts. So we can see that, well, it's not too far out, but I guess it's enough. This is greater than that, whereas the pion is in between both the electron and the half of proton. So therefore, that must be the exchange particle. And we already know that, don't we? But we've just proven it. Question 2. This looks like photoelectric effect. Current is measured only when radiation frequency greater than a certain value, blah, 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 blah. Why does the frequency of the radiation have to be greater than a certain value? Well, we just need to write down what we know about the photoelectric effect, nice and easy. Metal has work function. Let's define that. It's the minimum energy required for electron to be liberated from the surface of the metal. We know that energy of photon is equal to HF. Therefore, frequency of photon must be large enough such that its energy is greater than the work function. There we go, only 2 marks, I think that'll do. Okay, we have this graph for 2.2 showing current against voltage applied. We have the stopping potential. What's the number of photoelectrons per second? Okay, interesting. So electrons per second. I think this is one of those cases where units are going to be our friend. Leaving the photoemissive surface when the current is at a maximum. Okay, so when the current is at a maximum, we're talking 30 microamps, so 30 times 10 to the minus 6. So we can say that's 3 times 10 to the minus 5 amps. Now, we're looking for electrons per second. And so what do we know that current is? Well, we know it's coulombs per second. An amp is a coulomb per second. So we need something else. Of course, we're going to need the charge of electrons. So 1.6 times 10 to the minus 19. And, well, that's coulombs, but let's write down coulombs per electron. Always find it useful with these kind of questions to write down your own bespoke unit. So now we have coulombs per second, coulomb per electron. So we want to end up with electrons per second. So we have coulombs per second, coulombs per electron. We know we want to end up with seconds to the minus 1. So that's going to stay the same. So we divide these this way round. So 3 times 10 to the minus 5 divided by 1.6 times 10 to the minus 19. And that gives us 1.875 times 10 to the 14 electrons per second. But seeing that we were given the data to 2 sig figs as per usual, we're going to say that's 1.9 times 10 to the 14. 2.3, we're being asked, why does the current top out? Well, let's have a think about this. If we have a PD applied across the anode and the cathode in the right direction, then we're sort of pulling electrons across to the anode. How does that actually help? Well, it helps because that means that you're actually sort of reducing the work function because the electrons are being sucked off the plate a little bit as well. They're being helped along. So what we can say is that at max current, max number of photoelectrons reaching the anode. Not a super easy question, this one. So the whole idea is that, well, at lower PDs, we have loads more electrons absorbing photons that are actually being released because of the work function, of course. And so we're almost counteracting the work function by having this PD across it. And so why doesn't it get any bigger? Well, that's because there's only so many photons going in, aren't there? So max number of photoelectrons depends on intensity of radiation, i.e. number of photons absorbed per second. Okay, why does I decrease as V becomes more negative? So as V becomes negative, we can say that work is being done on the electrons in the opposite direction. So they are less likely to reach the anode. And why is that? It's because they have range of energies. We should probably say kinetic energies. Let's say what happens when the current goes to 0, when EV is equal to EK max. So let's say that the maximum kinetic energy that an electron had was 1 joule, way too much, but just an example, 1 joule. Then when E times V, that is the charge of an electron times the potential, is equal to that 1 joule, then we're counteracting the kinetic energy that it would otherwise have. 2.5, repeated with a different surface, smaller value of the work function, so phi is smaller. Source is unchanged. What's going to be the effect on the stopping potential? Well, let's write down the equation. We know that EK max is equal to HF minus phi. So therefore, if phi is smaller, EK max will increase. Therefore, higher stopping potential needed to reduce current to 0. In other words, they need less energy to escape, so that means they're going to have more kinetic energy. We need a higher PD to mitigate that. Question 3. Why are the 2 loudspeakers coherent? Well, to be coherent, 2 sources must have constant phase difference. That's the posh way of putting it. Now, in order to have a constant phase difference, then they must be the same wavelength as well, same frequency, doesn't matter which one you say. And again, that's sort of redundant, because in order to have a constant phase difference, then they must be of the same wavelength anyway. So I don't like the fact that they expect you to put that second point as well when one qualifies the other. So again, AQA being a bit too picky. How is this achieved? Well, it's achieved because they are connected to the same signal generator. I mean, that makes sense, doesn't it? Fairly easy. 3.2. Student faces the loudspeakers. That's A. A is equal distances from P and Q. He moves to point B, still facing the loudspeakers. Why do they make this so complicated? Just say he moves along the line. Good grief, whatever. As his head moves, the amplitude of the sound decreases and then increases. Amplitude starts to decrease, blah, 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 blah. Basically, we're just being asked to explain why do we get interference. So, at A, it's all to do with path difference, isn't it? Whenever we have double slit experiments or something like this, same thing. At A, path difference for waves arriving at A, that is, whatever, is equal to 0. Therefore, they interfere constructively, so like this, to increase amplitude. Between A and B, path difference is equal to half a wavelength. Therefore, waves are pi radians out of phase, 180 degrees out of phase, doesn't matter. Therefore, interfere destructively, amplitude decreases. And then at B, path difference is equal to lambda, constructive interference occurs. We're being asked to find the path difference. You might be tempted to use the Young's double slit equation here, but here's the issue. I've seen questions like this come up a lot recently over the last few years. The Young's double slit equation only works if the big distance, the slit screen distance, as it were, is a lot bigger than the slit separation. When it comes to loudspeakers and things like that, we're talking about quite a big distance between the loudspeakers relative to the screen distance. Yes, the screen distance is bigger, but not by much. So therefore, the equation breaks down. So just be careful. In these kind of situations, you don't want to use the Young's double slit equation. You'll have to think about things trigonometrically instead. So you're going to have to crack out Pythagoras. Let's have a look at these distances here. So we have 0.3 in between. So therefore, that means that this distance here is 0.15 meters. Let's draw a couple of dotted lines going across here as well. So we're looking for the path difference. So ultimately we need to find this distance here and then this distance here. This is 0.15 meters going down there. Okay, fine. So let's deal with our blue triangle first. So we know that this up here is going to be, well, what was it? 0.95 take away 0.15 then. So that's going to give us 0.8 meters. Okay, and we know the big distance here, of course, is 2.25. So therefore, we're looking for this distance 1, let's say. So distance 1, just using Pythagoras, 2.25 squared plus 0.8 squared. It's a lot of effort. Good grief. And that gives us 2. Let's go to 2 decimal places. So that's 3.9 meters. And then our orange triangle, well, that's going to be 0.95 plus 0.15. So it's going to give us 1.1 meters. And then we have the 2.25 there as well. So our distance 2 there is equal to the square root of 1.1 squared plus 2.25 squared. And that gives us 2.50 meters. So therefore, difference between them is going to be 0.11 meters. So that's our path difference there. 3.4 then, we're just being asked to find the speed. So we know speed, C or V, whatever, V is equal to F lambda. So that's going to be 2,960 times our 0.11. And that gives us 360 meters per second. 3.5, okay, he moves to C. The frequency is decreased. Okay, so let's just have a think. If the frequency is decreased, then that means that the wavelength is increased. That's the important thing here. What effect will that have on the amplitude of the sound as he's there? Okay, so let's just say, first of all, past B, amplitude will be low, as the path difference going to be about, I don't know, let's just say it's between, wish they'd put it a little bit further up so we could say it's a half, but whatever. the path difference is between, what did we say, lambda and 2 lambda. If the wavelength does increase, that means that the path difference will decrease because the wavelengths are bigger, so that path difference doesn't have as much of a difference, as it were. So path difference decreases. So as it gets closer to lambda, the amplitude will increase, again due to the constructive interference. And then we can say it will decrease again when lambda gets even bigger. I don't like waves questions. I love waves, just don't like their questions. Let's go on to something a little bit more tangible. We have 2 cameras, and is the average speed of vehicles. Ugh, I hate these. I should never have to go 50 on a motorway, whatever. So we're being asked what the average speed of the car is. Well, that means that we have to find the total distance divided by the total time. That's going to find us the average speed. So let's find out the total distance. Of course, we're going to find the area under the graph, aren't we? 1.5 there, and we also have 2.5 there. Now, this is in minutes at the minute, but let's just leave it as is for now. We can just times the whole thing by 60 at the end. So I have this trapezium here. So let's say that that's 15 plus 24 divided by 2 times by 1.5. I have this trapezium here, so that is going to be 12 plus 24, that's 36, I'll write it down anyway, times by 1.5. I think I can tidy that up actually in a minute. Plus this here, just going to be 1 times 24, so 1 times 24, just 24. So this is going to be 39 divided by 2, so it's 19.5. But let's do the 12 plus 24 divided by 2, so that's 36 divided by 2, so that's 18. And that's times 1.5, just factorizing here. And then we add on the 24 at the end. And so we end up with 80.25. All we have to do then is times that by 60. And we end up with 4,815 meters. Okay. All we have to do then is divide that by our time. So that's going to be 4 times 60, so 240 seconds. So we end up with 20.06, so 20.1 meters per second. So speed limit is 22 meters per second. So this driver is A-OK. We have chevrons. Typical reaction time is between 1.6 and 2 seconds. Suggest a value for D where the speed limit is that. What's interesting is that actually it's not 1 chevron apart, it's 2 chevrons apart. You're supposed to keep your distance at, but whatever. Let's go with the time as 2 seconds. Let's err on the side of caution. We know that the speed limit, and so the speed is 31 meters per second. And so we're looking for a distance. So we have speed equals distance over time, therefore distance equals speed times time. So let's say that's 31 times 2, so that gives us 62 meters. Brakes of the car applied, comes to rest, total mass of the car is that. Okay, so let's write down our data. We have a speed of, or rather I should say, a U initial speed of 31 meters per second. Braking force is 6.8 kilonewtons, I'm going to say 6,800. So we want the time taken for the braking force to stop the car and the distance traveled by the car in this time. Okay, so we know that force is equal to the rate of change of momentum. So therefore, rearranging this, time is going to be equal to delta mv. It's going from that 31 meters per second to 0 meters per second. So we can just say that, well, the change is just that initial value. So 1,200 kilograms times the speed of 31 divided by the force of 6,800. That is 5.5 seconds. We're looking for distance as well, therefore we're going to use our work done equation. Work done is equal to FD. How much energy is required? Well, it's going to be the same as the kinetic energy of the car. So we can say half mv squared is equal to force times distance. So therefore, all we have to do is pop force under the other side. So distance is equal to, let's just put the mass there, mass times velocity squared, divided by, I'm just putting the 2 underneath there, 2 times 6,800. And we end up with, let's do 2 sig figs, 85 meters. Wowzers, 85 meters to stop. I don't buy that. I've got better brakes than that. Of course, for the time, you could have said that acceleration is equal to change the speed divided by time and then use F equals ma. That's just the same thing as what I've done. 4.4. Why does the separation not take into account distance travelled as a car comes to rest after they've pushed the brakes? Yeah, that's an interesting one. I'm not sure I buy this question actually, but the whole idea is that, well, if the car in front of you brakes, then they're still going to be travelling. And so if you're behind, then you're going to be braking a little bit afterwards, but you're both going to be travelling at the same speed essentially. I don't think this question is right. So, but what the mark scheme is looking for is that it assumes car in front braking is still moving. The whole idea is that it hasn't really stopped dead, so therefore you do not have to stop where car in front started. But I'm not sure about this one because I was under the impression that actually those chevrons were there. So let's say the car in front doesn't brake and they go smack into the back of another car, you have enough time and enough distance to come to a standstill before that. So I'm not sure about that, but maybe that's where the whole 2 chevron thing comes in. I don't know. Okay, 4.5. We have a bend. This looks like it's going to be a circular motion question, and indeed it is. We have a mass of a car, 1,200 kilograms. We have an angle of 5 degrees. We have a radius of 200 meters. Very easy to get confused with these questions. So first things first, we're going to write down the weight. We're going to put the weight on there. Then we have the normal reaction force going up here from the ground. Effectively, what we're being asked is what is the centripetal force going horizontally? That's our centripetal force. So a couple of ways that you can do this. Now, if you know me and you know my videos, you might have seen my easy vectors trick video, and I say that I don't usually like drawing triangles, and that is true. But this might be one of the few times where it is actually useful. So first things first, we know the car is being kept up. So a component of this reaction force must be pointing upwards, and we know that must be equal to mg. Now, if that's theta there, then that's theta there as well. I mean, you can tell just by looking at the angles, but you can prove it with triangles if you are so inclined. So the thing is that the normal reaction force here is the biggest force. It's the resultant force. That's not true if we just have a mass on a slope, but because we have it going around a banked curve, we have this normal reaction force being bigger than the weight, bigger than mg. So therefore, if we take F up here, then we have a nice right-angled triangle. So we know mg. What do we know F is? We know it's a centripetal force, so this must be equal to mv squared over r. So therefore, what can we say? We know that tan theta, because we have the opposite and adjacent, is equal to the opposite mv squared over r divided by mg. And so the m's cancel, and this ends up just being v squared over gr. Rearranging this, we're looking for v. V squared is equal to gr tan theta. And so that means that obviously v is equal to the square root of gr tan theta. So it's the square root of 9.8 times 200 times tan of 5 degrees. Make sure you're in degrees, not radians. And we end up with a speed of 13.1, but let's just say 13 meters per second. So the trick with these questions is always, first of all, to flip mg. Always flip mg, whether it's a car on a bank track or it's a plane that's banking, always flip mg. And then you have your triangle of forces. Question 5, we have electrical power transmission using DC. Okay, what do we have? Power supply of 12 volts. So EMF is 12 volts. No internal resistance, fine. So we can just say that's V total, as it were. And we have these lamps that are 12 volts and 1.5 watts each. And there's 3 of them. Okay, so what are we being asked to find? Find the resistance. Nice and easy. We know that power is equal to IV. We don't have current. So actually, let's replace that with V over R. So we end up with P is equal to V squared over R. Swapping these two around, R is equal to V squared over P. So that is 12 squared divided by 1.5. And we end up with 96 ohms, so about 100. 5.2, we have 2 short copper wires. Calculate the current in the power supply. So we have power is equal to 1.5 per bulb, so that's times 3, so let's call that 4.5 watts. And we know that P is equal to IV. We're looking for I, so we can say current is equal to power divided by PD. So that's going to be our 4.5 divided by the 12 volts. And we end up with 0.38 amps. So as per usual, when it comes to electricity, you've just got to remember what you're looking at. We're looking at, in this question, the total current, because that's the current flowing through the battery. So just think about it. Do you have the total voltage? Yes, we do, 12 volts. Do we have the total power? Yes, we do. So that's what we're going to use. You could also find the total resistance. That would make life a little bit more difficult, but you could do that and figure it out from that. 5.3. So we're now replacing the copper wires with constantan. So we're looking for the resistance. Le résistance, we have the length of each wire is 2.8 meters, but then we have, oh no, each length, okay, fine. We have the diameter is 0.19 millimeters, so I'm going to change that into meters right off the bat. It's 1.9 times 10 to the minus 4 meters, and then we have the resistivity is 4.9 times 10 to the minus 7. Of course, we need to have the area. We might as well calculate the area. We could do it all in one go, but you know, it's a 3-mark question, so let's do it bit by bit so we can pick up some marks even if we get the final answer wrong. So area is equal to pi r squared or pi d squared over 4. That's pi times 1.9 times 10 to the minus 4 squared divided by 4. And that gives us 2.8 times 10 to the minus 8 meters squared. Sounds about right. Then all we need to do is plug this into our equation. Resistance is equal to rho L over A. That's 4.9 times 10 to the minus 7 times 2.8. 4.9 times 10 to the minus 7 times 2.8 divided by the area, which you said is 2.8 times 10 to the minus 8. Oh, I can probably tidy this up. So minus 8 on the bottom. So we can just say that that's 49 on top. And wait, we got 2.8 and 2.8. Cool. So that just ends up being 49. Surely not. What do you know? Didn't even need a calculator. How cool is that? Answer, not very. Right, 5.4. It's intended to show the lamps are dimmer when using constantan. Discuss whether the demonstration achieves this and support your answer with suitable calculations. Okay, so resistance of wires equals 49 times 2 because we have 2 of them. So 98 ohms. Right, and we saw that the resistance of each lamp is 96 ohms, but what we need to say is total resistance of the lamps is equal to 3 times 1 over 96. So in other words, the resistance of the lamps is equal to 96 over 3, so 32 ohms. Okay, so in essence we now have a potential divider. We have the resistance of the lamps, we have the resistance of the wires. So let's see what the PD lost across the wires is then. So it's going to be 12 times, well, this 96 divided by the total resistance. So that's what, 128? Oh, what do you know? That's bang on 9. So that means the PD across the lamps is going to be that 3 volts that's left. That's nice. So yes, we could then compare that to the 12 volts, etc. We can say that V is 4 times smaller. Therefore, if we know that power is equal to V squared over R, then actually power is 16 times less. So yes, they will be a lot dimmer. So therefore, the demonstration does work. You could do it in terms of currents as well. That's also acceptable. 5.5. Superconductors, nice and easy. Advantage, no resistance. Therefore, no energy lost due to heat arising from resistance. Disadvantage, need to be cooled to below critical or to critical temperature. Let's just say to critical temperature to achieve this. This requires a lot of energy to achieve. So basically it's pointless. All right, multiple choice. I love it. Question 6, mechanical power. Is it a vector? Is it measured in joules? Well, we know it's not measured in joules because it's watts. Has a base unit of kilograms, meters squared. Okay, so let's figure this out. I mean, it's not D, is it? Force times distance moved, that's not power, that's work done. Let's have a look. Power is equal to force times speed times velocity, and we know that force is mass times acceleration, so then power is MAV. We know acceleration is speed divided by time, so that's v squared. So what do we have? The units of this is kilograms, meters per second times meters per second divided by seconds. So actually we end up with, yes, kilograms, meters squared, seconds to the -3. That is correct. When it comes to it being a vector, we know that work done is a vector, isn't it? Because work done is across a distance, so it has to be in a certain direction. Or does it? Bit of a weird one, that one. But yeah, in that case, looking for the most correct one, C is correct. Water waves are given by this, where K is a constant. What's possible unit for K? Okay, so V squared is equal to K lambda. Therefore, K is equal to V squared divided by lambda. So therefore, the units of this, lots of units going on here, it's going to be meters squared seconds to the -2 divided by meters. So therefore, we just end up with meters seconds to the -2. So it looks like it's going to be A. 8, we have a photon of energy that 1 times 10 to the 18 electron volts. Object has a mass of 0.03 kilograms. How's going to equal to? Oh, okay, right. Well, first things first, we need to turn that into joules. So times that by 1.6 times 10 to the -19. Don't need a calculator for that. We're just going to end up with 0.16 joules. So EK, half mv squared, is equal to 0.16. So therefore, speed squared is going to be 0.16, 2 times that, divided by the mass we said, that's 0.03. So 0.32 divided by 0.03. So that's going to be 32 divided by 3. And so if we square root that, then we end up with 3.3 meters per second. So the answer is B. Deuterium, nucleus, tritium, nucleus, fusion, blah, 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 blah. What is X? Well, it's not going to be an electron, is it? It's not going to be a positron, because this doesn't involve any leptons. So what do we have here? We have a mass of 5 going to a mass of 4. But we have proton numbers just staying the same. So we've lost a neutron. So therefore it is going to be a neutron that has been ejected. The answer is B. Number 10, we have thorium, and it decays by alpha and 2 beta. So 232, doing an alpha, we end up with 228 and 88. And then we have 1 beta that takes us up to 89, and then another beta that brings us up to 228 and 90 again. So we're going to end up with, oh, it's thorium again. What do you know? So the answer is C. Number 11. Oh, easy. What quantity is measured in kilowatt hours? I mean, this is in the news at the minute everywhere, isn't it? It's energy. It's C. Alrighty, number 12. Electron collides with an atom, raises electron to a higher energy level. Okay. A, the colliding electron is captured. No. It's not. B, it just bounces off, doesn't it? A photon is emitted when the electron rises. No, that's the opposite, isn't it? It's only when it de-excites. C, an electron is emitted when it... No, electron isn't emitted, a photon is. So it has to be D. Let's just check it. The colliding electron transfers energy. Yeah, that's correct. Gives energy to the other electron. 13. What graph shows the variation of momentum? Lambda is h over p, so therefore lambda and p, momentum that is, are inversely proportional. So you should know that a y equals 1 over x graph looks like this. It is asymptotal, so A and B look quite similar, but it's not going to be B because that touches the y-axis, so the answer is A. 14. Monochromatic light. What happens to the wavelength, speed and energy? Okay, so glass into air, we know that the speed increases. And we know that because of V equals F lambda, if the speed increases, so does the wavelength, but the frequency stays the same. So we know wavelength increases, so it has to be A or D. So it's not B or C. So speed increases, that's the same for both as well. Photon energy, the photon energy doesn't change. You can't just randomly have a higher energy for the photons when they go from glass to air. You're getting energy for nothing. That is not possible. 15, wave travels across water. So we have amplitude. Oh, okay, right, that's all it's asking us. W is amplitude, and then Z is wavelength, because it's not time period, because this is a distance graph, not a time graph. So therefore the answer has to be A. Easy peasy. 16, wave on water. Okay, so we have V is equal to, let's change that to meters, 0.24 meters per second. Amplitude is the wave. We don't care about the amplitude really, do we? No, trying to throw us off. Frequency is 4 hertz. Okay, well, let's find out the wavelength real quick anyway. So wavelength is equal to V divided by F, or C divided by F, or whatever. So that's going to be 0.2. I don't even need a calculator for that. So 0.06 meters. Okay, let's have a look at the answers. A, the phase difference between P and S is pi over 2 radians. So they are 3/4 of a wave out of phase. And so that's the same thing as a quarter of a wave. And so yes, that is pi over 2 radians out of phase. So A must be correct. Let's just check the other ones. B, distance between P and R is 6 centimeters. No, it's half a wavelength, not a whole wavelength. C, particle velocity at Q is maximum. No, it's going to be at 0, because that's when it goes from up to down. So it is going to be going from positive to negative at that point. It's 0 at that point. D, particles at P and R are in phase. No, they are completely out of phase, in antiphase, or pi radians out of phase. 17, unpolarized light. We have 2 filters, blah, 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 blah. So we're spinning Y. So we're turning it in terms of radians. Oh gosh, okay. When are we going to have the next intensity? Well, it's when it's spun half a circle. So it has to be pi, right? So it has to be pi, 2 pi, 3 pi. So it has to be C. Stationary waves. We have a length of 1 meter. Which statement is not correct? A, first harmonic has a wavelength of 2. That is correct, so that's not our right answer. Because remember, we have half a wavelength on our first wave, our first harmonic. B, the midpoint of the rope is always stationary for even numbered harmonics. Yes, that is true, because for even numbered, we're going to have in the middle a node, so B is correct, so it's not a right answer. C, a harmonic of wavelength 0.4 meters can be set up on the rope. Let's rub this out real quick. Well, let's have a think about this. So if we have 0.4 meters, then we have 0.4 meters, it's one wavelength, 0.4 again, and we end up there, and then we have another 0.2. So we are going to end up with 1, 2, 2.5. So we do have a multiple of half of the wavelength, as it were. Therefore, yes, that is possible. So that's not a right answer. Has to be D then. Let's just check. There are 5 nodes on the rope for the fifth harmonic. No, that's not true, is it? Because the number of the harmonic tells you how many loops you have, not how many nodes you have. So for the fifth harmonic, we have 1, 2, 3, 4, 5, 6 nodes. So therefore, that's our right answer, because it's wrong. 19, we have this diffraction grating that is 4.5 times 10 to the 5 lines per meter. Let's change that into an actual grating spacing. So that's 1 over 4.5 times 10 to the 5. And that gives us 2.2 times 10 to the minus 6 meters. Okay, so there's our equation. However, they have tried to catch us out as per flipping usual. They've given us the angle between the second order diffraction maxima. Oh, my days. So here's N2 on the left-hand side, here's N2 on the right-hand side, so our second orders. This is 44 degrees, so actually just one side is going to be 22 degrees. That's how they've tried to trick you. I nearly fell for it. I can imagine that probably 90% of people who did a question fell for it as well. At least that's what I'm going to tell myself. So we're looking for lambda, so lambda is equal to d sine theta divided by, and so that's going to be 2.2 times 10 to the minus 6 times sine of 22 divided by 2. So I guess I can just call that 1.1 times 10 to the minus 6 times sine 22. And we end up with 4.1 times 10 to the minus 7 meters. So I can see the answer is going to be B. We have this question on moments. Which one of these is correct? Is the rod in equilibrium? Well, let's just have a look. First of all, how much force we have going up. 20 newtons going up, 20 newtons going down. So forces check out. What about the moments though? Well, let's take moments about the middle there. So we have 0.3 times 6 on the left-hand side. So therefore, that's going to be 1.8 Newton meters. That's going to be anti-clockwise. And then going clockwise, we have 0.2 times 4. So that's going to give us 0.8 Newton meters. So no, it's not in equilibrium. For equilibrium, an anti-clockwise moment of 1 Newton meter is needed. Anti-clockwise, no, that's not true. We need a clockwise moment. Oh, so there we go. C is the next one. Yes, because we have 0.8 here, 1.8 there. We need an extra 1 going clockwise. Small water drops, leave a tap, blah, 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 blah. Okay, intervals of 0.2 seconds, right? They then fall freely 0.8 meters to reach a horizontal surface. They then fall 0.8 meters. Okay, well, this is going to be SUVAT then, obviously. So what do we have? We have a distance of 0.8 meters. We have U of 0. Don't care about V as per usual. A is 9.8. We want to have time first of all. So let's go with S equals UT, but UT disappears. So let's just say half AT squared. And so if we're looking for T is equal to the square root of 2S over A. So it's going to be the square root of 1.6 divided by 9.8. Seems like a lot of work, this question. We end up with 0.4 seconds. I'm sure that's fine. Okay, so it takes 0.4 seconds to reach the ground. But then how far has a drop fallen when the previous drop hits the surface? Right, so basically we are talking about a time of 0.2 seconds then. All right, so again, let's do S equals half AT squared. So that's half times 9.8 times 0.2 squared. And that gives us a distance of basically 0.2 meters. So I think the answer is B, and it is. What a bizarre little question. Pellet velocity of that into a block. Okay, we know that this is a momentum question, of course. So we have a V of 200 meters per second. I should probably say U, but whatever. Let's have the mass of our pellet of 5 grams. I don't think, we don't need to turn that into kilograms because it's all relative. Fired upwards into a stationary block. Oh my days, what is going on in this question? So pellet goes upwards and the mass of the block is 95 grams. Impact causes, okay, what's the maximum vertical displacement of the block? So we need to know the initial speed of the block here once the pellet has embedded itself in it. So we know that total momentum before equals total momentum afterwards. So we can say that MP, I'm just going to call it VP of the bullet, is equal to the mass of the block and the pellet inside it. We're going to have to add that on times the speed of the block. So therefore, we're just going to divide by the mass of the block, yes, and the pellet. Let's pop that on there. Why not? So that's going to be 5 times 200. Again, it doesn't matter that we haven't turned it into kilograms because it's just all relative, divided by 100. So therefore, it's just going to be 5 times 2. And so that's just going to be 10 meters per second. And so then we're just going to use SUVAT to get the total distance moved. So let's write down SUVAT. We're looking for S. We know we have a U of 10 meters per second. V is going to be 0 at the apex. And we have an acceleration of minus 9.8 meters per second squared. One of those times where you do have to be careful with your positives and negatives. So we're going to use, well, kind of, but not really. V squared equals U squared plus 2AS. And so therefore, we're going to say that V squared is going to be 0. So effectively, U squared equals 2AS. Yes, we have minuses in both of those. So S is going to be equal to U squared divided by 2A. So it's going to be 10 squared divided by, well, 2 lots the acceleration, so basically 20. So 100 divided by 20. So it should be 5 meters. And it is. The answer is A. Okay, so quite high, doesn't it? A lot of work for that question, though. That's usually sort of like a 3-4 mark question in the rest of the paper. 23, electric motor lifts a load of weight W in height H, blah, 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 blah. What's the efficiency of the motor? We've seen this time and time again. We know that efficiency is useful power, useful energy, doesn't matter. Useful energy out divided by total energy in. Of course, we're lifting this block, so it's going to be the work done in lifting it. So it's going to be force times distance, where it's going to be mgh, isn't it? Where mg is the weight, so therefore it's going to be wh. So this is equal to wh divided by the total energy in. So there's going to be v times I times t, because this is power. And so therefore the answer looks like it's going to be A. 24, simple harmonic motion. I was wondering when this would come up. What's the total energy of the particle? Well, this comes back to V max. Our equation for this is 2 pi F A. And so therefore, if we're looking for kinetic energy, it's going to be half mv squared, where V is that V max. So it's just going to be, well, the half. Let's put it all in. So therefore, half m times 4 pi squared F squared A squared. Half and the 4 cancel just to make it 2. So it looks like the answer is going to be B. 25, mass of 0.9 kilograms. Suspended, we have a K of 80 newtons per meter. When the mass is displaced, it undergoes vertical oscillations, blah, 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 blah. What is the frequency of the oscillations? We know that the time period is equal to 2 pi times square root of m over k. So therefore, if you want the frequency, I guess we could do it all in one go. Just flip the whole thing. So we end up with that. So just replacing all of this, and we end up with 1.5 hertz. So the answer is C. 26, experiment carried out with young modulus. Blah, 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 blah. What's the gradient of the graph represent? So let's have a look. What have we got? We have extension here. I don't know, let's call that E, delta L, X, whatever you want to call it. And we have the force here. And we have a nice straight line. So let's get our equation out. We know that the Young modulus is equal to FL over A delta L, or AE in this case. So we have F over E, but our gradient is going to be E over F. Therefore, rearranging this, we end up with E over F is equal to L over EA. So our answer is going to be D. 27, one of these setups. Okay, when the temperature is increased, well, first things first, we know that when we increase temperature, the resistance of a thermistor will go down. If that goes down, so does its share of the voltage if it's in a potential divider situation. So what's going to happen? Which change to the circuit will restore the voltmeter to 0? Okay, so let's have a look at A, first of all. A reduction in the EMF of the cell. No, that's nonsense, isn't it? That doesn't matter at all. It's all relative. A reduction in the resistance of P. No, that's not going to do it either as well, because if we have P there and Q there, the voltmeter in between, if the resistance of the thermistor is going down, we'd need Q to go down to balance it out, both sides, because we need the potential at this point and this point on both sides of this setup to be the same. So it's not going to be B. C, an increase to the resistance of Q. No, that's going to be the same thing as a decrease in the resistance of P. So it has to be D, but let's check it. A reduction in the resistance of R, yes, that is going to have the same effect, because, well, let's say that this goes from, I don't know, 5 ohms to 1 ohm, then that means that we need this to go from, say, 5 to 1 ohm as well. So they have the same relative PD across both of them as a sort of potential divider setup. 28, here we have 3 cells all connected in parallel. And we have this resistor. We're being asked for the total resistance, that is the resistance going through R. What is the total EMF going to be? Well, it's just going to be E. We're not summing the EMFs because they're in parallel, but because they all have an internal resistance, we need to know what the combined resistance of these 3 internal resistances is. So we can say 1 over little r total is equal to 1 over R plus 1 over R plus 1 over R. So basically equal to 3 over R. So that means that we have the total internal resistance of all 3 of these is R over 3. And then you might be tempted to go for the internal resistance equation, EMF, but at the end of the day, if we're looking for the total current and we've got this complicated setup, it is just V equals IR just for the total values. So therefore, if we're looking for this, then we can say that I is equal to V over R. So that is equal to E over, and what's the total resistance of the whole thing? We are looking for the total resistance. It's going to be this R over 3. Let's just say the R first, the resistance of that load resistance plus R over 3. And now this is what caught me out. This is what stumped me for a while. So I was like, well, that's the right answer. None of those seem to look like the right answer, but they've just multiplied both top and the bottom by 3. And so it is going to end up being we end up with 3E divided by 3 lots of R just plus little r. So that might have caught you out like it did me. 29. So we have here the voltmeter is V, but when the switch is closed, it becomes V over 3. So that is the terminal PD. What's the internal resistance of the cell? So we know that R is 2 ohms. So let's have a think about this. So we know that the PD, the terminal PD, has gone down by a factor of 3. So that must mean that the 2 ohms is getting a third of the EMF, or the total voltage. And so that means that the battery must be getting 2/3 of the total voltage. And so therefore, if we have 2 ohms on the resistor there, then we must have twice as much inside the battery. So it's going to be 4 ohms. The answer is C. And then finally, 30. Period is doubled when the pendulum length is increased by that much. Let's get our equation. T is equal to 2 pi root L over G. All we're concerned about is T is proportional to root L. So let's say T squared is proportional to L. So therefore I can say that T1 over T2 all squared equal to L1 over L2. We know that time 2 is double. So therefore this whole thing turns into a quarter. So that must mean that the length has also gone up by a factor of 4. So therefore, if it was 1.8, therefore if it's gone up by 1.8 meters, then that must mean that, well, what was it to begin with? But that means it's times by 4. Then that means that the original length must have been 0.6 meters. If you want to prove that though, you can do it the long way around. You can say that 1/4 is equal to L over L plus 1.8. L plus 1.8 equals 4L. So therefore 3L equals 1.8. Therefore L is 0.6 meters. That's your lot. I hope you found that helpful. If you did, please leave a like. And if you want to have a look at the rest of my papers, then click on the card and it'll take you to the playlist. I'll see you next time.